Okay, sorry. So I was just setting a couple of things up. Now that's working. So let's begin with our next topic. So until now, we're done with the basic arithmetic. We've talked about a number of different things already. For example, what are the different types of numbers, how to deal with fractions. Then we talked about BODMAS, and then how to find difference between numbers, and then ordering numbers. In the last class, we also did some examples. And then at the end, I just told you that you need to make sure that you remember all of these different powers of these integers. Uh, for squares, ideally, you should know up to 20 square, but at least up to 15 squared. And for cube, ideally up to 10 cube, but at least until 5 cube. Okay. This is what you need to memorize because that's going to be needed for the non-calculator paper. Okay. Now, let's start with the next major concept that we've got, and that's algebra. Now, before we deal with algebraic expressions, there are some indices rules that you need to know of because they often come in handy when we are dealing with algebra, because a lot of times you have to simplify expressions that might look like this, for instance. So, for instance, you have 5 raised to the power x into 2 raised to the power 4x divided by 3 raised to the power 2x. If you had to simplify something like this, and maybe in the denominator you also had 25 raised to the power x, if you want to simplify this expression, you need to be able to simplify indices, right? You need to be able to work with indices. Now, how do you do that? That is what we want to start with first, and then we'll talk about some examples on this and also the factorization process. So this week, our focus is going to be on algebra, and that is going to cover like 20, 25 marks across the two papers that you've got, some in paper one, some in paper two. So let's begin with this. Let's start with indices first of all. So what are indices? It's basically when you have a power on something. So for instance, you have 3 raised to the power 4. Now, this number 3 is your base number. This is the base. And this number that you've got on top there, this number is the power. Okay. You can call it a power. You can also call it index, and indices is just the plural of index. Okay. So index is singular, plural of that is indices. Okay. Now you need to know some basic rules for indices that you would need to use in simplifying and different types of expressions that involve powers like this. For instance, let's start with the first rule. If you have two numbers multiplying, let's say you've got a times a, one of them has power m and the other has power n. How can you simplify them? You see, the bases are the same in both of them. A and A, bases are the same. When bases are the same, powers get added. Okay, you have two numbers multiplying with bases the same. What happens to the powers? Powers are going to get added here, and it becomes a raised to the power m plus n. For instance, if we have something like this, 3 raised to the power 2x multiplied by 3 raised to the power 4. You can write this as 3 raised to the power 2x plus 4. Okay, so the bases are the same. What happens to the powers? They get added. Okay, that's the first rule that you've got for indices. If you've got two things multiplying, bases are the same, powers get multiplied. You can just write that down in words as well. When bases are same, powers get added. And what's the operation that's applying? let me actually write it like this. So you've got multiplication that is happening here, and you've got same bases. You've got multiplication, bases are the same. If the bases are the same, then powers are added. Okay. Now, very similar to this, we've got another rule. If you have a raised to power m divided by a raised to power n, you've got two things dividing like this. Now, in this case, you've got division, and again, the bases are the same. What happens in this case? The powers get subtracted and you get something like this, a raised to power m minus n. For instance, if you have 2 raised to power 5 divided by 2 raised to power 3x, you can write this as 2 raised to power 5 minus 3x. You've got two things dividing, their bases are the same. What happens to the powers? The powers get subtracted. Okay. So what's happening in this case? In the second rule, if you have division happening and the bases are the same, in case of division with same bases, powers get subtracted. Okay. Now, this was the first one, and this is the second one. These are two rules that you need to know about. Now, let's think about this. Let's say you've got 4 raised to power x plus 4 raised to power 3. How do you apply these rules here? Any idea? What do you get as a result from of this? 4 raised to power x plus 4 raised to power 3. Can you simplify this? If you apply this rule, does this work? So if you're sending messages in the chat box, please make sure to do that to everyone so I can see that on my other account. Otherwise, I will not be able to see that. Yes. What do you think? Bases are the same, right? However, we've got addition here. This is not going to be 4 raised to power 3x. This would be wrong. Okay. This rule does not apply here. This rule does not apply here. You have to be very careful. This is a very common error that happens in the exam. These rules that we got for indices, they only work when you have multiplication or division. They do not work when you have addition or subtraction. Okay. They do not work when you have addition or subtraction. So you cannot do anything with this. You cannot simplify this. This does not work. So in general, if you have a raised to power m plus a raised to power n, that does not give you anything. Okay. And similarly, a raised to power m minus a raised to power n, that also does not give you anything. So if you do something like this, a raised to power m plus n, or a raised to power m minus n, that would be wrong. You cannot do it like this. Okay. So these rules only work. I can write that down here. The indices rules only work when we have multiplication or addition. They do not work when we have, multiplication or division. They do not work when we have addition or subtraction. Okay, they only work in this case. All right. Okay, now let's move on to the next one. So these are two similar rules. Multiplication, bases, when bases are the same, powers get added. And in division, when bases are the same, powers get subtracted. Okay. Let's move on to the next one. It looks like this. If you have something like this, a raised to power m divided by a raised to power n. We already talked about this, in fact. Let's make it this. If you have a raised to power m divided by b raised to power m. Now, in the previous case, we had bases the same, right? What about this case? In this case, the powers are the same, right? When powers are the same like this, we can write this as a whole power. We can say this is a over b whole raised to power m. For instance, if we had 2 raised to power 5 divided by 3 raised to power 5, that's the same thing as saying 2 over 3 whole raised to power 5. Okay. Similarly, if you've got multiplication here, it works the same way with that. If we have, for instance, a raised to power m multiplied by a raised to power n, again, a raised to power m multiplied by b raised to power m, the powers are the same, but the bases are different. You have multiplication. What happens to the power? You can write this as a whole power like this: a into b whole raised to power m. You can write it as a power that that's on the whole thing. You multiply the bases. Okay. So it's kind of like taking power common, right? You can have the power on the whole thing. What would be an example of this? You could have something like this, for instance, 5 raised to power 3 into 3 raised to power, or let's use a different number, let's say 4 raised to power 3. That's the same thing as saying 5 times 4 whole raised to power 3, which means that's 20 raised to power 3. They mean the same thing. If the powers are the same, we can kind of write it as a whole power. Okay, you can take power common in a way. That's the next rule. Now, in this case, again, you've got to be careful. This taking power common things, this only works when you've got multiplication and division like this. If you've got addition or subtraction, again, that does not work. For instance, if you have a raised to power m plus b raised to power m, that's not the same thing as a plus b whole raised to power m. That would be wrong, right? Just like when you do a square plus b square, that's not the same thing as a plus b whole squared, right? You know how to expand a plus b whole squared. How does that work? A plus b whole squared is a squared plus 2ab plus b squared, right? So this does not work like this. Is that okay? Similarly, if we've got subtraction, if you have a raised to power m minus b raised to power m, that's not the same thing as a minus b whole raised to power m. You cannot take power common here. You can only do that when you have multiplication or division happening. This also does not work. Similarly, if you had a square minus b square, you know that cannot be written as a minus b whole squared. These are two different things. A square minus b squared, in fact, is a plus b multiplied by a minus b. And this thing is actually a square minus 2ab plus b squared, right? So these are two different things. So these rules only work with addition, with multiplication and division. All right. Now, these are very important. A lot of students end up making these mistakes through their A levels as well if they're not, if the foundation is not right. So let me know if there are any confusions here. Is this all right? Any problems with this?
It's clear so far, sir.
Okay. Now, this works both ways. You can go in the right direction. You can also go in the other direction. You can also say, if you have a into b the whole raised to power m, you can split the powers and write it like this. Similarly, this also works both ways. If you have a over b whole raised to power m, you can split it and write it like this, and that also works. And in this case, of course, does not work. A plus b whole raised to power m does not expand to this. A minus b whole raised to power m, that does not expand to this. These are wrong. Okay, this does not work. Similarly, the ones on the right side, these are also not correct. These are not possible. Okay. All right. So that's the indices rules that we've got. Then there's another one. So the first type of rule that we did was when the bases were the same, right? Now, the second type of rules that we did is where the powers are the same. Okay. Now, the next type is when you've got something like this, a raised to power m whole raised to power n. For instance, you could have 4 raised to power 2 whole times 3. Now, how do you simplify this thing? This is the same thing as saying 4 raised to power 2 times 3, and that can be written as 4 raised to power 6. Okay, so you can have this power and a power on top of that. Okay, what happens in this case? The powers get multiplied. All right, if you have a power and you have a power on top of that, these powers get multiplied. So if you have a raised to power m whole raised to power n, that becomes a raised to power m times n, like this. Okay, similarly, if you have, in this case, for instance, this is an important thing to remember. If you have 4 raised to power 2 and then whole power 3, that becomes 4 raised to power 6. You could also have it this way: 4 raised to power 3 whole raised to power 2. That can also be written as the same thing. That's 4 raised to power 3 times 2, and that also becomes 4 raised to power 6. Okay? So this power can be switched as well. If you have a raised to power m and then whole raised to power n, that's also the same thing as a raised to power n whole times m. These are all the same. Okay? You can switch these powers with each other as well, and that also works. Now, you have to be careful here with this error. If you have a raised to power m whole raised to power n, that is not the same thing as a raised to power m plus n. Do not add these powers. This careless error happens a lot, that when people have, for instance, x raised to power 2 whole raised to power 3, they end up writing this as x power 5 because they confuse this with this previous rule that we did when the bases were the same and powers were getting added. Here we had two different expressions that were multiplying, right? We had two bases that were equal. We added the powers there. That's not the same thing as this. This is only one expression, and you have a power on top of a power. You do not add the powers here. The powers get multiplied in this case. Okay? So the powers get multiplied in this case. This is going to be wrong. You cannot do it like this. All right? Okay. Now, sometimes you have to deal with negative powers as well. What do you do with them? If you have, for instance, a raised to power minus m. Negative powers can be written like this. You can take them to the denominator and write them like this: 1 over a raised to power m. So for instance, if you had 2 raised to power minus 3, you can write that as 1 over 2 raised to power 3. So that becomes 1 over 8. Okay, so if you have negative power, you can take the reciprocal of that. Okay. Similarly, if you had a over b whole raised to the power minus m. For instance, if I were to give an example of this, you could have 2 over 3 whole raised to the power minus 4. If you want to make this power positive, you can write it as a negative power. You can also write it as a positive power. How would you do that? How do you do that? You can take 3 to the numerator. You can take 2 to the denominator. You can switch these numbers, right? And then what does that become? That becomes 3 over 2. The sign of the power is going to change in this case, and that becomes power 4. Okay, so when you have a negative power, basically you take reciprocal of that to make the power positive. So in this case, if you have a over b whole raised to power minus m, you can write that as b over a whole raised to power m, and that's the same thing. Okay, so if a lot of times we need to make the powers positive, that's a nicer way of writing things generally. Although both are correct, this is also correct, this is also correct, but you should know how to go from one form to the other. Okay, this also works both ways. If you have 1 over a raised to power m, you can write this as a negative power. If you have b over a whole power m, again, you can write this as a negative power like this as well. So all of these rules that we run for indices, they work in both directions. All right. Okay. So these are all the rules that we've got in indices. Now there's some special cases after that. So these are the rules that we discussed. Okay. Bases are same and the numbers are multiplying. What do we do with the powers? We add the powers. Bases are same and we are dividing the numbers, powers get subtracted. Powers are the same and the numbers are multiplying. You have a whole power there. Powers are the same and the numbers are dividing. Again, you can take power common like that and it works both ways as well. If you have a power on top of a power, you multiply the powers like this. And then finally, if you have a negative power, you can take reciprocal of that to make the power positive. Okay. Now we've got some special powers that have some properties. For instance, if you've got any number raised to power 0, if you have 6 raised to power 0, what's that? That is 1. Okay. That's a general rule that we've got. If you've got anything raised to power 0, the result of that is 1. Okay. Why is that though? Why is that though? Does anyone know? Why is anything raised to power 0, 1? Just think about this. You can kind of understand a pattern to figure this out or to intuitively understand why this has to be the case. So think about it. If you had 6 power 1, what would that be? That would be 6, right? 6 power 2, what would that be? That would be 260. That would be 36. And then 6 power 3, for instance, would be 216, and so on. You can find powers of 6 like this. From this, we can kind of get a general rule like this. We can say if we have 6 raised to the power n, as in 6 could have any power n, and we multiply that by 6, what's the result supposed to be? The result is supposed to be 6 raised to the power n plus. Can you guys still hear me? I think I got disconnected from my other device.
Yes, sir. We can hear you.
Okay. There's something wrong with the other device. Just give me a second. Recording in progress. Okay, I'm sorry I got disconnected. Can you see my screen again? You can see my screen again, right? Okay, sorry about that. Okay, so basically, you can have a rule like this. If we have, for instance, 6 square into 6, what does that give us? That gives us 6 cube, right? If we have 6 cube into 6, what would that be? That would be 6 raised to power 4. So we can generalize that and we can say 6 raised to power n times 6 should be 6 raised to power n plus 1, right? Now, what if n was equal to 0 here? What do we get from that? We get 6 raised to power 0 multiplied by 6 equal to 6 raised to power 0 plus 1. And what does that give us? 6 raised to power 0 into 6, that equals 6 power of 1. The 6 will go to the other side, get divided there. and we get 6 power 0 equals 6 power 1 over 6, and 6 power 0 turns out to be 1. So for all of these values to work, 6 power 0 has to be 1 for this general rule to work. 6 power n times 6 being equal to 6 power n plus 1, power 0 has to be equal to 1. Okay? Now, that's basically the logic behind it. But now you need to remember, whenever you've got anything raised to power 0, the result is equal to 1. For instance, if you've got 6 power 0, the result is 1. If you've got any other number raised to power 0, the result is 1. 3 raised to power 0 is 1. 9 raised to power 0 is 1. Minus 5 raised to power 0 is 1. So anything raised to power 0 is equal to 1. Okay? What about this? Minus 4 raised to power 0? Remember BODMAS? Power gets evaluated first, right? Before the negative. This will be minus 1, right? Because 4 raised to power 0, that evaluates to 1. And we have minus with that. This is going to be minus 1, right? So, but anything raised to power 0 is equal to 1. All right? Okay. Now, there's an exception here, and that is that A cannot be equal to 0. Okay? A cannot be equal to 0. Now, why is that? We will talk about that once we have discussed the next thing first. For instance, if you have 1 raised to power anything, so 1 raised to power m, let's say, this is always equal to 1. Okay? 1 raised to power anything is equal to 1. 1 raised to power 5 is equal to 1. 1 raised to power minus 3 is equal to 1, right? Anything that comes as a power of 1, the result is always equal to 1. Okay? If you have anything in terms of x in the power, for example, you could have 1 raised to power x plus 3. Now, whatever that is, this is going to be equal to 1. So 1 raised to power anything is going to be equal to 1. What about 0 raised to power anything? Let me add that here as well. 0 raised to power anything is equal to 0. Okay, so 0 power 3 is 0. 0 power minus 2 is 0. You can have any power on top of 0. The result is equal to 0. Now, let's look at these two rules now. We know that anything raised to power 0 is equal to 1, right? Anything raised to power 0 is equal to 1. And 0 raised to power anything is equal to 0, right? If the power is 0, the result is 1. And if the base is 0, the result is 0, right? Now, what happens if we have 0 raised to power 0? What about this? We've got two rules there, right? Anything raised to power 0 is equal to 1. 0 raised to power anything is equal to 0. Which rule do we apply here? If we apply the first rule, anything raised to power 0 is equal to 1. This should be 1. If we apply the second rule, 0 raised to power anything should be 0. It should be 0. So which one is it? This is actually undefined because there's ambiguity here. We don't know if it's going to be 1. We don't know if it's going to be 0. So it's basically undefined. It does not have any value. If you try to put this on your calculator, you will get an error for this. You can try that, 0 raised to power 0. You'll get a math error from your calculator because it's not defined. Okay? All right. So these are some rules that you need to keep in mind. Anything raised to power 0 is 1. 0 raised to power anything is 0. And 1 raised to power anything is equal to 1. Now, sometimes you can have powers that are in fractions as well. So for instance, you could have 4 raised to power 1 over 2. You could have fractional powers like this. Now, what does that mean? This denominator can actually come outside, and you can write it like this. You can say this is square root of 4, like this, right? Square root of 4. What is that result? What does that result in? That gives you 2 as the result. 2 is the answer. Okay. If you have, for instance, 27 power 1 over 3, this 3 in the denominator that you've got, that can be written as a cube root here. So this 3 goes there and becomes the root, and that gives you 27. What's the cube root of 27? That is 3. How do you figure that out? Because you'll remember that 3 cube is equal to 27. So if you want to take cube root of 27, that results in 3. So in general, if you have something like this, a raised to a power 1 over m, what can you write that as? It becomes root a with m being here. Okay, whatever that number is in the denominator, that comes as a root here. Now, sometimes you can also have powers like this. You can have 3 raised to a power 2 over 3, for instance. Or you can actually use something that you can actually evaluate. So let's say 27 raised to the power 2 over 3. What if you've got something like this? This 3 that you've got here, that can go and become the root. So this will go and become the root. And inside you have 27 square left. So you can write it like this. Okay. Now, how do we generalize that? If we have a raised to the power m over n, this can be written as nth root of a, and you have power m on top of that. So the denominator of the power, that becomes the root, and the numerator, that comes as a power here. Okay, so generally we use n for the root, and use n here. It doesn't really matter. If you have whatever is in the denominator, that is going to go outside and become the root there. Does that make sense? For instance, now if we had to simplify this, sometimes you have to evaluate this, right? Evaluate 27 raised to the power 2 over 3. How would you do that? You can say that is 27 raised to the power 2 over 3. How do you simplify this? One way to do that would be that you say it's cube root of 27 squared, and you've got 3 outside like this. But the problem is, this becomes a bit hard to evaluate now, because how do you evaluate 27 squared? You can either, write it down like this and do that multiplication and then take cube root of that. That's one possibility. Another way to simplify this could be that we write it like this. First of all, if we have to simplify this, let me write it down first, that we want to simplify 27 raised to the power 2 over 3. Now, if we directly write it that way, it becomes fairly complicated, right? Because we have to evaluate 27 square for that. How do you make it simpler? You can break the power down like this. You can say that is 27 power 2 and 1 over 3. So we can write them as multiplication like this, right? Or we can also write it outside using that rule that we discussed earlier, a power m whole raised to power n. We can write that as a power m times m. So this power 2 over 3, we can break it down into 2 parts. We can write one part inside the bracket and one part outside the bracket. And now when we do it this way, we can evaluate the cube root of 27 first. 27 raised to power 1 over 3. What's that? That is cube root of 27. And then we have whole square on top of that like this. Now, this is something that we can do, right? Cube root of 27, what's that? That's 3. So 3 squared, that results in 9. So when you have a fractional power like this, you actually can break it down into two parts. And when you do that, it becomes simpler to evaluate. Okay? Another way to think about this could be that you write 27 as a cube. You could also do it this way. You have 27 raised to the power 2 over 3. You could say 27 can be written as 3 cube, right? We know that 27 is a cube of 3. And then outside, we've got the power 2 over 3. And now what happens is these powers have to multiply, right? Again, using that rule, that a raised to power m whole power n, that is a raised to power mn. So we can say it becomes 3 raised to power 3 times 2 over 3. And now 3 and 3 actually get cancelled, and we're just left with 3 squared, which is 9. This is another way of thinking about that same thing. Okay, so we should be able to evaluate expressions like these, numbers like these when they have fractional powers. Okay, so that happens using indices rules as well. Okay, now what if you had to simplify something in which we have decimals involved? So you saw a couple of questions like that in the arithmetic worksheet earlier as well. I think there was one which had cube root of 8. How do you evaluate that? If you had cube root of 8, for instance, what is that? Sorry, not cube root of 8, decimal. So decimal was 0.008. If you had to evaluate this, now this is a bit hard to evaluate because you only remember cube root of some integers, cubes of some integers, right? Like 1, 2, 3, 4, 5, and maybe up to 10. But what about cube root of 0.008? That's hard to evaluate. What you do is, using the tricks that we learned in arithmetic, we can actually write 0.008 as 8 over 1000, right? We have 3 decimals, so we can have 3 zeros in the denominator like this, and then you have cube root of this whole thing. Okay, now what's cube root? Cube root is just a power, right? It's like saying 8 power 1 over 3, or in fact, 8 over 1000 whole power 1 over 3, right? Using indices rules, we can say this power can be split because we've got division, right? So we can split it like this. We can say this is 8 power 1 over 3 over 1000 power 1 over 3 because we have division. If we had addition or subtraction, we could not have done that. So this cube root can actually be broken down into two parts, and you can write this as cube root of 8 over cube root of 1000. Now, what's cube root of 8? That is 2. Cube root of 1000, that is 10. And that simplifies to 1 over 5, or in decimals, that will be 0.2. That's the result that we get from this. Okay, so that's how you could evaluate powers of decimals, that you first write them as integer fractions, and then you evaluate the result from that. Okay, I hope that makes sense. Now, that's how you deal with fractional powers or cube roots or square roots. Now, a lot of times you have to solve equations involving indices as well. Okay. For instance, since we're talking about fractional powers right now, if we had x raised to the power 2 over 3, and that was equal to, or in fact, let's make it simpler first of all. Let's say we had x raised to the power 2, that was equal to 16. What are the values of x that you get from that? You take square root of both sides, right? You take the power 2 to the other side. So it becomes x equals 16 power 1 over 2, right? So basically, we apply the same operation. The idea is that we want to apply the same operation on both sides. So since we have x squared equal to 16 here, what we're looking to do is we want to find the value of x from that. This power is 2. We want to make this power 1. How do you make this power 1? You take square root on both sides. Or you can say you raise both sides to the power 1 over 2, right? You apply the same operation on both sides. You take power 1 over 2 on both sides. When you do that, on the left side, you've got 2 and 2, and they get cancelled, right? And on the right side, we've got 16 power 1 over 2, and that results in 4. However, there's a catch here, and that is whenever you take square root, you also have to put plus minus there. Okay, so this results in 4, but there has to be plus minus 4 there because when you take square root, your calculator is only going to give you one result. However, we know when we multiply two negative numbers, the result becomes positive. So minus 4 into minus 4 is 16, and 4 into 4 is also 16. So when you take square root on both sides of any equation, we consider both possibilities that we could have a positive answer or we could have a negative answer. So we have to consider both plus and minus. However, in order to remove the power, that's what you would do. You would basically take square root on both sides like that. Okay. Now, similarly, if we had another equation, it might be like this, that you have x raised to the power 2 over 3, and that is equal to, or in this case, let me take something else. That would not work. Could it work with, yeah, let's try x power 3 over 2, and we had, let's say, 64 on the other side. Okay, x raised to power 3 over 2, that equals 64. How do we solve this equation? Solving means we want to find the value of x that satisfies this equation. How do you find that? The idea is we want to get rid of the power 3 over 2 from here. How do you do that? How do you get rid of this power 3 over 2 from here? You raise both sides to power 2 over 3. Okay. Why? Because when we do that, 3 and 3 will get cancelled, 2 and 2 will get cancelled, and on the left side, we would just be left with power 1. And that's what we want, right? So we had x power 3 over 2 equal to 64. What we did was we raised both sides to the power 2 over 3, because on the left side now, we get power of 1, and that's what we wanted. On the right side, we've got 64 raised to the power 2 over 3. And now how do we evaluate this? 64 raised to the power 2 over 3. How do we think about this? One way to do this could be that we write this 3 as a cube root, and then we have a whole square on top of that. And that would give us cube root of 64, which is 4, right? 4 cube is 64. So this gives us 4, and then we have square there, and the result turns out to be 16. Or another way to think about the same thing could be like we did before, we could write 64 as 4 cube, right? Because we want to get rid of this power in the denominator. And then that becomes 4 cube power 2 over 3. 3 and 3 will get cancelled, and we're left with 4 raised to power 2 again, and the result turns out to be 16. In this case, we do not put plus minus because we're not taking a square root, we're actually taking a cube root. Okay? In cube root, we don't put plus minus there. In even roots like square root, fourth root, we have to put plus minus, because in that case, there's a possibility of getting negative results as well. Because negative numbers, when multiplied even number of times, the result turns out to be positive. Okay, so you have to keep that in mind. When you take square roots in equations, you have to put plus minus. When you take cube roots in equations, you do not have to take or put plus minus. Let me write that down here. In equations, when you take roots on both sides, for even roots, for example, square root, fourth root, sixth root, you put plus minus on both sides. For odd roots, for example, if you have cube root or fifth root, you keep the same sign. That is already with the number. Now, what do I mean by that? If you have, for instance, x squared equal to 9, you take square root on both sides or raise whole both sides to the power of 1 over 2. It's an even root, right? You're taking square root. You have to put plus minus. So this becomes x equal to plus minus 3. If you have x raised to power 4 equal to 16, again, it's an even root. When you take fourth root on both sides, right, it'll be an even root. You can say it's fourth root of 16. You have to put plus minus there, so it becomes plus minus 2. For even roots, you put plus minus like this. And if you have odd roots, for instance, if you had x cubed equal to 125, you take cube root on both sides, the result is just 5. The original number was positive, the result is also positive. If you had x raised to the power 3 equal to minus 27, now in this case, the original number is negative. When you take cube root of this, minus 27, the result is going to be minus 3. So if the original number is negative, the answer is negative when you take cube root or fifth root. When the original number is positive, the answer is also positive. For square roots and any other even roots, you have to put plus minus. Okay. For negative numbers, we cannot take square root or fourth root. For negative numbers, the even roots do not exist. For instance, square root of minus 4. This is not possible. Square root we can only take for positive numbers. But for cube root or fifth root, we can take them for both positive and negative numbers, and the result is going to be same as the original number. If the original number was positive, the result would also be positive. And if the original number was negative, the result would also be negative. All right. Now, using these indices rules, you need to be able to solve some other kinds of equations as well. For instance, you will have an equation like this. Let's say you have 5 raised to the power m multiplied by 5 raised to the power 2, and that is equal to, let's say, 5 raised to the power 8. Now, what's the value of m that you get from that? How do you solve this? On the left side, you've got two things multiplying. One way to do this is that since the numbers are multiplying, you say the bases are the same, so the powers get added. So you have 5 raised to the power m plus 2, that is equal to 8. Now, since you have the same bases, what you can do is you can say the powers should be equal, and then m equals 6 from this. That's the value of m that you get as the result. Okay. If you have, for instance, 7 raised to the power 2x minus or in fact, can't do that, multiplied by 7 raised to power 4, and that is equal to 7 raised to power 10. What about this? Again, on the left side, the the bases are the same, and we have multiplication like this. What happens? You can add the powers, so it becomes 7 raised to power 2x plus 4 equals 7 raised to power 10. And now what you can do is, you can say, since the bases are the same on both sides of this equation, the powers should also be the same. So you have 2x plus 4 equal to 10, and that gives you 2x equal to 6 and x equal to 3. That is the final result that you get from this. That's the value of x that we get. Okay. Now, you can only equate the powers here like this if you have the same base and you have only one term on both sides. You can't have multiple terms. So for instance, it would be wrong to just say after this step that since the bases are the same for all the terms, you just say 2x multiplied by 4 because we've got multiplication here, that equals 10. That would be wrong. You cannot do it like this. This does not work. You would first make the base the same, and it should be a single base. First of all, you should only have 7 on this side and 7 on this side, only one term on both sides. And then you can equate the powers. You can say 2x plus 4 here should equal 10. You cannot equate them when you have multiple terms on both sides. Okay. So when can you do this? You only equate powers when there is a single term on both sides. That's important. There should be only a single term on both sides. And that is equal. Okay, so there should be only one base on both sides, and they should be equal to each other. When you have multiple, then we can't do that unless we first make them one. Okay, that's how we solve equations involving indices. Now, this was where we had multiplication. Sometimes you have division as well. You could have something like this: 8 raised to the power x divided by 2 raised to the power 3. Let's say that is equal to 2 raised to the power 4. What if you've got something like this? How do you solve this equation? Now, can we apply any indices rules on the left side here? Powers are different. Bases are also different. Now, in order to be able to use any of those rules that we have learned, we either need the powers to be the same or the bases to be the same. At least one of those things has to be true for us to be able to simplify this. Okay. Now, how can you make it the same base for all the numbers? What's 8? 8 is basically 2 raised to power 3. So we can write this as 2 raised to power 3 whole power x divided by 2 raised to power 3 equals 2 power 4. Okay, so we can write 8 as 2 raised to power 3. So it becomes something like this. What do we do next? Remember, we can't cancel these out. Okay, that does not work because this 2 raised to power 3 just has power. This is just 2 raised to power 3. This 2 raised to power 3 has this power x as well. You can't just cancel it out like that. So what do we do after this? The numerator, we can write that as, we can simplify that as 2 raised to power 3x, right? These powers get multiplied. What about this power in the denominator? Let me show one more step here. 2 raised to power 3 equals 2 raised to power 4. We can say this is 2 raised to power 3x minus 3. We have bases the same and we have division here. So the powers get subtracted. On the other side, we've got 4 here. Alternatively, you could also just multiply this 2 raised to power 3 on the other side and make it 2 raised to power 7. That is also possible. You could also have done that. Now we've got a single term on both sides, 2 raised to power something, 2 raised to power something, and both the bases are the same as well. So what we can do is, since the bases are the same, we can equate these powers. We can say 3 raised to power x minus 3 should equal 4. So that gives us 3x minus 3 equals 4, this equation, and 3x equals 7. And the value of x from that turns out to be 7 over 3. This is the solution of this equation. All right. That's the solution that we get for this particular equation. It's 7 over 3. All right, so you should be able to solve equations that look like this. Let me give you another example. Let's say we have 10 raised to power x equal to 0.001. How do we solve this equation now? Now, we've got something in power. Whenever we've got a variable in the power, x in the power, what we want to do is we want to make the bases the same on both sides. Right now, we've got 10 raised to power x on the left side. On the right side, we've got this decimal number. Can we somehow convert it to a power of 10? How do we think about this? Let's first of all write it as a fraction to make things simpler to understand, because we find it hard to deal with powers of decimal numbers. Now, how can we write this as integer numbers? We can say this is 1 over 1000, right? We've got 3 decimals here. So we have 3 zeros in the denominator like this, 1 over 1000. Okay. Now, what is 1000? 1000 is basically 10 raised to the power 3, right? That's 10 cubed. And now, if I want to bring this power to the numerator, what happens? When you take reciprocal, the power is going to change its sign. So it becomes 10 raised to the power minus 3. And now we've got the same bases on both sides. That means the powers are supposed to be equal as well. So x should equal minus 3. And the result that we get from this is negative 3. And that is our final answer. That's what we were looking for. Okay. Is that all right? So that's how we
Yes, yes.
solve equations involving indices. Okay. All right. Now, let's take another example. So this was equations. Let's say we had to simplify things. So I also mentioned that earlier. Let's do a couple of examples of that now, because we will not be able to start factorization. We'll do that tomorrow. For now, let's quickly go through this. What happens when you have to simplify some expressions? So a lot of times you have to do some simplification of some fractions or some products that involve indices. Let me actually quickly look for an example on that. Just give me a second. Paper 1, algebra. Okay, I'll just write an example where we have to simplify something. Okay, so let's say we've got something like this: 9x y raised to the power 6 whole raised to the power 1 over 2. Or in fact, we've got a whole raised to the power 1 over 2 here, such that in the denominator, we've got x cubed y squared. We need to simplify this. Okay. Now, what does that mean? How to simplify this? We want just one x and just one y, and the powers should be simplified, right? Right now, we've got this whole power 1 over 2, and there's some powers inside as well. We've got multiple y we've got multiple x's. We want to simplify all of this. Now, how do we do this? Let's keep this outside power as it is for a while. Let's simplify what we've got inside. What do we have inside? We have 9. Okay, so there's nothing that we can divide in the denominator. We don't have any other number in the denominator as such right now. So we keep it as it is. What about x? In the numerator, we've got x power 1. In the denominator, we've got x power 3. So we can write this as x power 1 minus 3. What does that become? That becomes minus 2. Now, this is your choice if you want to write this as a negative power or as a positive power. Generally, we actually prefer it as a positive power. So you can also write it like this, that the bigger number is in the denominator, the bigger power is in the denominator. You can in the denominator, write it like this, that you have power 3. If you take this power from the numerator to the denominator, you can write this as 3 power minus 1 as well. So it works both ways. You can do it in the beginning or you can do it at the end. I'll show you both ways. One possibility is that we write it like this on the left side, or we could write it like this in the numerator, the x term. Okay. Then what about y? The bigger number is in the numerator, that's 6. The smaller number is in the denominator, that's 2. So this becomes y raised to power 6 minus 2. And then you have whole power 1 over 2, or alternatively, you could have y raised to power 6 minus 2 here, whole power 1 over 2. Okay, all right, now let's simplify this. So it becomes 9y raised to power 4 divided by x power 2, whole raised to power 1 over 2. And similarly here, if you were to do it the other way, you would have 9 raised to power x minus 2, y raised to power 4, whole raised to power 1 over 2. You can do it any one of these two ways. They're all right. They're both correct. Now, what do we do next after this? We have this power 1 over 2 on the whole thing, right? We have power 1 over 2 on the whole thing. What do we do with that? We have to multiply that power with the powers inside. Okay. Now, this power comes on 9 first of all. That becomes 9 raised to power 1 over 2. It comes on y, and we have 4 into 1 over 2. That's 4 over 2 in a way. In the denominator, we have x raised to power 2 into 1 over 2. Now, 9 raised to power 1 over 2, what's that? That's basically square root of 9. That is going to be 3. Y raised to power 4 over 2, that's just 2. In the denominator, 2 into 1 over 2, that's just x. And we have 3y squared over x. That is the simplified form of this. And that's our final result. If you were to do it the other way with a negative power there, that's also possible. You could say this is 9 raised to power 1 over 2. And then x raised to power minus 2 into 1 over 2. And then y raised to power 4 into 1 over 2. Now, what happens to the powers? 9 raised to power 1 over 2, that means square root of 9, that's just 3. X raised to power minus 2 into 1 over 2. What does that become? That's x raised to power minus 1 into y raised to power 2. And then at the end, what you could do could be that you make this power positive. How do you do that? You take that to the denominator now, and you get the same result at the end, 3y squared over x. And that's your final answer. Okay, so you could do it both ways. You could deal with negative powers and then make them positive at the very end. Or in your working, you just keep everything positive by subtracting the smaller number from the bigger number and then simplify that. Okay, let's take another example. Let's say we've got something like this. We want to simplify 3a squared times b divided by 12ab raised to power 4. And we have whole raised to power negative 2. We want to simplify this thing. Okay, how do we do this? How do we do simplification of this? Again, let's deal with what we've got inside the fraction first of all. Let's simplify what we've got inside. Okay, so inside, first of all, the numbers, we have 3 and 12. We can cancel them out and get 1 over 4 from that. Okay, and then we have 1 over 4. What about a? A squared in the numerator, a in the denominator. That becomes a raised to power 2 minus 1, right? When you have no power, that means the power is 1. And then for b, the bigger power is in the denominator. So what you can do is in the denominator, you can write b raised to power 4 minus the power that you have in the numerator, that's 1, and then whole raised to power minus 2. Okay, let's simplify this further. In the numerator, we've got a power 1. In the denominator, we have 4b cubed, and then whole raised to power negative 2. Now, what do we do with this power negative 2? It makes things simpler if we make this power positive, first of all. So we can take the reciprocal of what we've got inside so that it becomes 4b cubed divided by a, right? And then the power becomes positive. And now we bring that power 2 inside to make it 4 squared into b cube whole squared divided by a squared. What's 4 squared? 4 squared is equal to 16. B raised to power 3 times 2. You multiply the powers, 3 and 2. What does that give you? That gives you 6. And in the denominator, you have a squared. And that's the simplified form for this. Okay, so that's how you do simplification of powers like this. All right, sometimes you have to do this with numbers as well. We haven't looked at an example like that. I'll just do one quickly. If you had, for instance, something like this, 10 raised to a power. In fact, that's actually very straightforward. Yeah, that's if you have 10 raised to power 3 minus 10 raised to power 0, if you've got expressions like these, you know how to simplify them. This 10 raised to power 3 is 1000, minus 10 raised to power 0 is just 1, and that gives you 999. So that's a different type of problem. Let me just do another, a bit complicated one before we end. Okay, let's do this. So let's say we have this from the worksheet again. We want to simplify this 2a squared b raised to power 5 divided by 18 a raised to power 4 times b whole raised to power 1 over 2. How do we simplify this now? Again, simplify what we've got inside the bracket first of all. What does that simplify to? What you've got inside the bracket. 2 and 18, they get cancelled, and you have 9 there. So you have 1 over 9. And then powers of a, you have a power 4 in the denominator. That's the bigger power. So you take this 2 down. So it becomes a raised to power 4 minus 2. For b, we've got the bigger power in the numerator. So it becomes b raised to power 5 minus 1. And then whole raised to power 1 over 2. Let's simplify this further. And this gives us b raised to power 4 divided by 9a raised to power 2. And now this whole power 1 over 2, we can bring that inside. So it becomes b raised to power 4 times 1 over 2 divided by 9 raised to power 1 over 2 into a raised to power 2 times 1 over 2. And now we'll simplify everything. B raised to power 4 times 1 over 2, that will be b squared. 9 power 1 over 2, that's basically the square root of 9. What does that give you? That gives you 3a raised to power 1. And that's the simplified fraction that we were looking for. That's our final answer. Now, it's not necessary to write all of these steps, but that's what you would be thinking in your head. You could skip a couple of these steps, and that's perfectly okay. But just make sure that you're not doing careless errors because of that. Okay, so that's the result that we get from this. I hope that makes sense. That's how we deal with indices. In the next class, we'll talk about how to factorize expressions and also how to solve quadratic equations. Okay, but that's it for now. We will continue from here in the next class. Now, these indices rules are extremely important. A lot of students end up doing a lot of careless errors because they don't have this concept right. So please make sure that you understand this well. I'll be uploading a worksheet of indices. Make sure to attempt that and let me know if you have any confusion. In the next class, we'll move on to how we can factorize expressions and then also how to solve how we can solve quadratic equations. Okay, so that's the next class. I'll see you again in the next one. If you have any quick questions, let me know. Otherwise, we end this here. Any problems, anyone? Any questions? No? All right. So that's it for today then. I'll see you again in the next one when we talk about factorization and quadratic equations. Okay. All right. Allah Hafiz, everyone. Please make sure to attempt the next worksheet now. I'll be uploading that. Okay. All right. Bye.
Thank you, sir. Bye.
Thank you. Allah Hafiz.